will be recorded, and we'll be sending out the recording of the webinar tomorrow morning with some additional resources and other Compliant Modeler videos to support some of the things we'll be going over today. So make sure you look for that email probably in the morning. I do want to point out in your interface for GoToWebinar, you do have the option of both raising your hand and sending in questions. We're going to be holding off on most questions till the end of the event, but I do encourage you to send them in throughout the entire webinar as they come up, as that'll help us prep which questions we're going to answer first. Some upcoming events we have. The next webinar will be the end of April, and we are going to be skipping May for webinars as we have our user conference. Now our user conference is 2.5 days, the 23rd through 25th, and is in downtown Detroit. It includes 18 presentations by different manufacturers from across the world, 2 training classes, 2 networking events, and skills and materials to take back with you. We have some specials going on right now if you participate in any 3DCS training class throughout the year of 2017. So make sure if you're going to be part of a training class, you mention that you'd like to join us at the Global Technology and User Conference downtown. If you only make one day, that's fine as well. We do recommend that you come on the Wednesday, the 24th, as we are having our banquet that evening. You can follow up with me after the webinar by filling out the survey if you'd like to get some more information on our Global Technology Conference. So I'm going to be really brief as we covered a lot of basic information and overview about Compliant Modeler at our last webinar. So Compliant Modeler is an add-on module for 3DCS. It's available in all versions of the software. It allows you to work with flexible parts rather than rigid body. So it is on top of a normal rigid body model. The way Compliant Modeler functions normally is by changing your nominal position of your parts to compensate for the forces and for the weight and for the applications of the compliant moves on your parts. And then you can do a traditional Monte Carlo analysis on top of that. As I mentioned, is available in all of our platforms, our integrated and our multi-CAD standalone platform. Today we'll be using our CATIA integrated solution, 3DCS CAA V5 based. And why do we use Compliant Modeler? As I mentioned before, we want to simulate our processes rather than just our rigid body tolerances. So processes that I'm talking about are clamping, welding, bending, gravity, thermal, and thermal from both environment and from outside influences. So if we have the exhaust system like we showed last time, during its function it's going to heat up more so on one side than the other side, and that's going to affect the way the components are joined and the actual dimensions of the components. Our presenters today, we have Maria Harangues, one of our senior variation analysts here at DCS. She is one of our FEA specialists. She'll be our primary presenter. In addition, I have Gary Bell, our ASME certified GD&T specialist, and Saurav Kakar, our other FEA specialist here at DCS. They'll be helping out with question and answer and are available in case you have any specific questions for them. So we're going to have Maria give you a quick recap of the last webinar by showcasing just some of the main compliant moves that were in the model, just so you can get up to date on what it is that we were talking about as we're building on some of those concepts today. All right, Maria, I'm going to pass the presenter over to you if you want to just give us a brief overview.
Sure, let me see. There it is.
There we go.
All right. So we did talk about the exhaust assembly last time, right? And we applied clamping and we attached the parts to each other, and then we applied gravity. And at this stage, the gravity is not applied. I'm going to turn on the gravity move and build them out, and you'll see how the parts drop being attached only at this end. And it shows you that the largest deformation is the tail end of the pipe. On top of the gravity, we also added thermal moves. The simplicity of the gravity is that in this move, you only have to add the parts that you applied onto and to set up the direction. For the thermal moves, I'm going to turn them on. A thermal move can be applied on the entire part, and you have to establish the change in temperature, which is in Celsius, and you also have to load the thermal file, which is generated with StiffJet. Once you set up all those parameters, applying the thermal moves will make the part deform differently. We did also attach the part in the direction here, but because of all these thermal moves, the deformation of the whole assembly changed, and the assembly deforms the most at this corner here.
So just to support you there, the color mapping we're showing is deviation from nominal position, right?
Exactly, yes.
Right. So because we clamped to the end, that's why that area is now green, because that's being held in place. But we're seeing the...
Yeah, let me turn off that move. So I'm just going to still let it hang.
Gotcha.
And then the deviation is again at the most deviation is again at the end of the pipe. But the pipe has grown due to the thermal moves applied on it. We could check the variation there. For example, with the thermal moves, the whole deviation is 23 millimeters. And if I turn off these thermal moves and build it without the moves, the deviation is 27. Well, it's shorter than it's nominal, so to speak, because it's dropped. So the thermal moves added about 4 millimeters in length. Yeah, this kind of summarizes the previous operations we used, thermal and gravity.
Thank you, Maria. I appreciate it very much. And as you mentioned, you are able to add clamp moves and to modify your model to compensate for some of that variation. And that's what you were showing us with that hang, right?
Yes, yes. We attach it back to the body at this location here.
Mm-hmm. And then I believe during the event as well, at the elbow joint where you showed the largest amount of thermal variation, I think you attached a clamp there as well to help compensate for some.
Here? Yes, yes. That clamp was created on the fly, so I could create that clamp on the fly, basically clamping this point here. I can add that. It's going to be a soft clamp, and I'll explain what that means. I'm going to add this point and attach it to the body and make this a soft clamp, meaning I am attaching it only in that direction. The other directions and the rotations are all free. So I'm going to add that move and turn on all the other ones, the hanging and the thermals, and build it now. Now you can see the deviation that was here larger, it was shifted again to the end of the pipe. Obviously, you cannot get rid of deviation or variation. You just push it around most of the time. So since we attached it in Z direction here, then this area is more stable, and it pushed the variation towards the end of the pipe.
Very good. All right, thank you, Maria. I'm going to take presenter back for a moment.
Sure.
All right, so that was just a quick overview of our previous webinar. I'll have a link to that in the follow-up email. The greatest value of it is that Maria went through all of those moves step by step. So it's an excellent webinar for new users of Compliant Modeler to get an overview of how to add compliant moves and some best practices. So today's primary agenda, we have two models for you. We're going to be showing joining, sequencing, and torque. So our first model is aircraft skin, where we're going to be joining two skin panels. So these are the two skin panels that we'll be joining, and you can see the different joins along the two panels. And when I say join, I'm talking about a compliant modeler move. A join move is a connection. It's going to bring two parts together and permanently connect them. So we use it to simulate spot welds, rivets, and bolts. And the reason we call it a join move and we don't call it a weld move is because unlike some welding processes, a join move just connects the two parts. It's not going to add a thermal effect. That would be a separate compliant move. So whether it's a rivet or a spot weld or a bolt, is going to consider them just joining the parts the same. And you can apply other forces to that, or you can apply gravity or other compliant moves on top of it. So what was the objective of this particular study? So we're answering two questions. Does the order of joins affect the overall variation? So if we start at the top and we do spot welds to the bottom, or we start in the middle and go out, or we start at the bottom, go to the top, or other different scenarios, are the scenarios going to have different amounts of variation? And then is there an optimal order of joins to reduce the amount of variation? So in practice, what we've done is we've taken a look at our points that we're going to be welding or connecting these two parts, and we're going to see, based on a number of proposed scenarios, which one is going to add the least amount of variation to our parts, and that's what we want to go with. So it's a method of optimizing our sequence to reduce variation. So the results. So we found, yes, the order of joins does affect the overall variation, in some cases more than others, and that allows us to find an optimal order of joins to reduce the added variation. So how do we get to these results, and which scenario is best? I'm going to pass presenter over to Maria so she can show you the model and just walk through how she came to those results. Maria?
Yes, I think everybody sees my screen. So I'm going to go into a little bit more detail on what Ben was talking about. The two panels are both attached to the fixture with clamps, and then there's two rows of welds between the two panels. The scenario that you see here, it's at the end of the line where there's the both panels are welded, joined to each other, and constrained at these 3 points, two on the left side and one in the middle here. The rest of the clamps, which you'll see everything else was clamped initially, they are released, so the panels will deform, and we measure at this corner and this corner, R1 and R5. And for these measurements, we have 4 scenarios. The first, I named them first, second, third, fourth. So you see first, second, third, and fourth. And what's the difference between them? The first scenario, it looks at the right side welding points. It does them in order from top to bottom, and then the left side welding row, it does it from top to bottom. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The second scenario is slightly different because it goes horizontally, so to speak. It goes right, left, from top to bottom. So different order of welding, joining. The third scenario is similar to the second, except for it starts joining from the middle of the panel and going towards the outside. So it does the middle, then the next above it, then the next below, and then the ends. And the fourth scenario, we do have this option to consider joining the right column first, and then the left column all points at the same time. So this would be only 2 join moves. The rest of them, they all have like 10 join moves. And then look at the variation of these two measurements. Plotted on a simple chart, it shows you this is the bottom measure at this corner, the top measure at this corner. There are obviously larger deformation at the top than at the bottom, mainly because the clamping point, it's not exactly halfway up, so this will vary more. But the third option seems to put the two variations closer to each other. So that should be, in my opinion, the most stable option. Starting like from the center and joining the points going towards outside, and joining the points at the same level, one next to each other, next to the other. So this is it in a nutshell. And to get to these results, I'm going to show you the model. The two panels and the fixture are joined. Let's see. First, we'll have the rigid body moves, which are simple fixed plane moves, and they are necessary for any compliant model. Then I did a different scenario for actually clamping the parts. For example, for the blue panel, I did separate clamping. First, I clamped the two top points, and then the rest of the points one after the other. So if you look at all the clamps for the blue panel, basically all the points are clamped to the two rails in separate clamps. And this can be a separate discussion about the order of these clamps. That can also change your results. For the gray panel, I put the clamps in just two operations, similar to the scenario 4 for the joining. I'm going to look at the first clamp. This one is a hard clamp applied on these two features. It's using the target associated vector, so whatever vector is on the target point, that's how this object will move towards the target. It's a hard OZOF, meaning once the object points meet the target plane, they stay there. There's no room for rotations or translations. The points are fixed relative to the target. The rest of clamps for the blue panel are soft clamps. And I mentioned this before, the soft clamps will constrain only in the direction of the vector. So the rotations and the translations in other directions are free. Basically, if you apply anything else, like a load or gravity or something to the part, this point, it's free to slide as long as the object stays in contact with the target point in that direction. So this is how the parts were constrained. After constraining the part, I applied a gravity on both parts. And I applied it in Z direction, so kind of let it sag. Basically, that assumes that it's building in this orientation. If you were to build them on their backs, so to speak, then gravity would be applied in minus Y. And that's another way of testing, see which way is better with less sag. Once the gravity is applied, I started creating the scenarios. The join moves, I'm going to go through one of them. It's applied on one pair at a time. It applies along the target vector. And this is a permanent operation. Once the points are put together, they will stay together. And the stiffness matrices of these two parts will be combined. The difference between, for example, this scenario where we have 10 join moves, one for each pair, and the last scenario, which has 2 moves, one for each scenario, where all the points on one column, one row are put in the same move. The difference between the two is that this calculates all the joins for the 5 points at the same time and calculates just one combined stiffness matrix. So it's one calculation versus 5. It will make things faster. For that reason, you want to usually consider the scenario and see if it's working. Going back to the Excel file, the scenario number 4 doesn't seem to be that great. I mean, there's more variation between these two, so I wouldn't necessarily recommend it. Back to the model. If I build a model, we'll see some deviations. We'll see where the deviation is the worst. Let's see. Oh yes, this would help. I had to turn the color contour on. So if you look at the overall deviation, there's deviation at these corners. There's some deviation here. The most of it is when it springs back at this area being still clamped in those 2 points. So that's another study if you want to check how that varies. I think, unless there's questions, I think this is it for this model.
Is that Maria? Is that gravity move? That's a compliant move, correct? From the previous,
yes.
Like from the previous webinar.
Yes, it's the same gravity move we applied in the previous webinar. It's applied to both skins, and it's applied in minus Z direction. So basically, we say that this assembly is built in this position, so the parts will sag this way due to gravity.
Gotcha. All right.
And yes, the gravity requires the mass matrix, which you loaded along with the stiffness and mesh file.
Great.
Okay.
Thank you. And then which scenario did you find to be the best?
In my opinion, this is where the 2 corners very closer to each other. So the top corner and the bottom corner are not twisting too different from each other. So I would go with the third scenario. The second scenario is not too far away from it. And keep in mind, this is all based on how the parts are constrained when they're joined and how the parts are still constrained after releasing everything. So basically how the parts relax when you unclamp most of the points.
Right. So you're considering how the welding and the joining affects them, as well as how they're going to relax after they're being released from tooling.
Yeah, so basically the clamping and unclamping, it's the same, but they will influence the numbers. But for this for comparison, they don't come in play. Just for the overall variation, they come in play. The comparison is just how this joining is made, in what order, and in what manner. So curves, no matter where they are on this axis, they are influenced by these four scenarios.
Perfect.
Does it make sense?
Yes. Thank you. Let me just check. So here's a quick question about the about the join move. So I think this question involves well, it's a welding point only related to a single mesh node. Do welds usually have a diameter?
Yes, it is one mesh node. If you have a diameter, you can pick. Well, there's more ways to do it. You can put RBEs to the edge of the hole, or you can pick a point on the edge of the hole and use that to join. You can put the point in the center of the hole. Let me see if I have that here. I am very sorry. Katia is not my friend today. You can put a point in the center of the hole, and that point will be linked to a node on the edge of the hole. That will give you a certain distance between point and node, but it shouldn't be a problem. So there's more ways to do this, but yes, it's one point. And I'm trying to launch Katia again. Are there any more questions about this, or we can maybe move to
I think we're going to move on. Hold
okay,
the other questions to the end. I'm going to take presenter back just for one quick second to show the other model we're going to be talking about today. So just to reiterate, in these scenarios, we found that the third order sequence, which was going down one side and then the other, I believe, or was that the one we went back and forth?
I'm sorry, yes.
Yes. So okay. Yeah, we got a couple of questions. We'll get to those. We're going to get to those after our next model demonstration. So from here, you can determine which scenario is going to work best, whether you want to compensate more for overall variation or if you want to compensate for the flex and twisting of the parts. So our next example is going to be the truck front end and torque involved with bolting the front fender onto the body. So our objectives, we're bolting at the front in two places to start. And does our order of operation affect the gap and flush conditions along the edge of the part? And which bolt should be done first? So which order should we do our process? And our results. So the order of operation does affect variation, and completing the front bolt first looks to have the lowest amount of influence. I'm going to pass presenter over to Maria so she can show you how she came to those results and confirm whether that's correct. All right, Maria.
Okay. There we are. I'm going to start again with the Excel sheet because it's easier to talk on it. A fender assembly, the fender outer, there's a bracket here and the reinforcement behind this area. They come as a compliant assembly, so I assembled them on a fixture on the side and then brought them to the body. The body I treat as rigid. And then once the fender is brought in, the bolts are going to be put into this hole here, and there's one here, and a couple of them here, and one behind inside there. Driving those bolts may deform the fender and twist it, so it may affect the gap and flush measurements here. I also took a measurement on the surface measurement here to see where this flange is going to end up. This flange is going to come in contact with the headlamp later on. These measurements, the gaps, the flushes, and this S4 measurement are plotted onto these 4 charts, which I'm going to explain to you a little bit. First chart represents the nominal values. This trend is the gap 1, 2, 3, and these dots here are representing the measurement S4. You can see that nominally, torquing the front bolt first or torquing the rear bolt first will not make a difference. They're about the same. But when we go to the actual variation of the gaps, that changes. It shows you that the green line, which is telling me that I'm torquing the rear bolt first, shows more variation for both the front point and the gaps than when I'm twisting and turning the front bolt first. So it looks to me like the best scenario is to torque this bolt and then get to this one. That's the way the gaps will have less variation. That can be translated in when you torque this bolt, you turn the fender this way. The fender ends up, let's say, in this direction, and I can show you on the model. And then we'll pull it back. When we pull it back, it does influence the variation here. Looking at the flush measurements, the 2 charts on the right, it doesn't show much difference between the 2, and that makes sense because we do have a locator here which pulls the fender in, so that controls the flush for this flange. So the flush is not going to be influenced of whatever happens with these bolts. Okay, and I'm going to, so this says 2 scenarios, what the difference would be between these 2 bolts. I'm going to go to the model and walk a little bit through the moves. Like I said, the fender is built off-site. These are the 3 parts that are put together, the fender outer, the bracket, and this reinforcement. Going through the animation, it will not basically cause much deformation. I'm going to skip ahead to the last operation that puts these bars together. The operations that happen in here are, we are holding the outer fender at its 3 datums. Then we're holding the bracket at its datums in the fixture, and similar locating features are used for the reinforcement. Once they're all held in place, these are all hard clamps. There's 3 hard clamp points that will not introduce any more twist in the part because we need 4 points to introduce twist in the part, basically. So they're just holding a part on their datum. And then we are going to start attaching the reinforcement. I'm using 4 different join moves, individual from each other. A few more, one at the top flange, basically securing the reinforcement. And for the bracket, I have points on these two flanges where they're going to be secured together. So once this is the bracket and the reinforcement are attached to the fender, all the three parts become one. And I'm going to take them out of this fixture and bring them into the next level where the fender assembly is going to be attached to this rails. Now the rails are way more sturdy than the fender assembly. That's one reason I treat the rest of the body as rigid. Another reason is because this is a smaller model, it's a stick-up model. It's very fast to build and you get quick results. And it wouldn't change the results much given the rigidity of this part versus this part.
Hey, Marie.
Next, yes.
Before we move to the next one, I just want to check again. So the hard clamps that you were using to hold these parts in their fixtures, what's the difference between the hard clamp and the soft clamp that you mentioned earlier?
Okay, so the hard clamp that I have here, for example, I'm using 3 points for them. You can use 1 point, it doesn't matter. But the idea of a hard clamp is once the object point, it finds the target plane, it stays there. It will not move anymore. It will not translate. It will not rotate. It's fixed relative to the target. If you make it a soft clamp will do the same operation to bring the object to the target point, but I'm going to cancel this. The only direction of constraining the object to the target is this, the associated target vector, the way we dictated here. You can also change the vector and you can make it any direction you want. You can choose a type in and then you make it any direction you want. But whatever direction you choose, that's the direction that your object point will be constrained. But it is free to rotate in all 3 degrees of freedom and to translate in the other 2 degrees of freedom. So basically 5 degrees of freedom are free. Okay?
Great, thank you. I just got a few questions about that, so I appreciate it.
Sure. All right, so that would be the fender subassembly. And I'm taking that subassembly and attaching it with a rigid move to the body. And after the rigid move, I'm going to use the fender attachments I used before. This is part of the best practices, coordination of datum and locators, right? Same 3 locators I'm using to hold this assembly now into a new fixture relative to the body. Once it's constrained, we apply gravity to, I'm applying it to all the 3 parts because they're all going to sag. And this settles the part, part and assembly as far as being constrained and its original shape because it's constrained here, but it wants to sag. So let me walk through the animation up to that point so you can see it better. Okay, so now the fender assembly is brought to the body. The next move would be the clamping, which I just talked about. The clamping will not do anything to it. The next one is the gravity, right? Once you apply the gravity, let's see, the part sags somewhat. You saw, I suppose you saw the points that were moving down. Then, now we start to use what's this model all about. So the next move, the next few moves, I'm going to actually constrain at 1, 2, 3, 4, 5 locations. All these are going to make the top flange sit on the rail. So let's see if it's possible to see it. It lifts them very little because the gravity didn't this is not necessarily a heavy assembly, so it didn't sag a lot. So once those are attached, I'm going to attach the other areas. This is the one that contributes to the flush measurement. This is the one that actually sets the flush. So this is attached also in Z direction. Everything is in Z direction for now. So up to this point, I'm going to show you. Up to this point, we have the clamp, the hard clamp, and basically setting the fender onto its locators. So touch condition here, and all of these other areas. Once this is done, starts the first scenario, for example. And I'm going to apply torque. So torque, the first scenario, it's torque at the front bolt. The second, it's torque at the rear bolt first, and then the other one. So the first torque, let me talk about torque a little bit. It is similar, in a way, the dialogue is similar to the force dialogue, and you can also find the force here, so you can swap between the two and apply a force instead of a torque. All you need for the torque is the points that you want to apply it to. You use this plus sign to add them, and the amount of torque, which is in Newton meter. Also, if you want to change the vector in which the torque is applied, if your point vector is not what you want, you can do so with the direction type. And that's all there is to the torque. Once you apply it, in this case, it's applied, let me show the direction, in minus Z. So that means it rotates clockwise. We screw the bolts clockwise. Okay, so let me show what the torque will do. And I'm going to go through animation to right before the torque. Okay, and then I'm going to apply the torque. You see the point shifted? Basically, it twisted the whole fender. Why it did that? Because I'm holding it here. So this point at this moment, it's not held in any direction except Z. So it tends to go that way. So to compensate for it, I'm going to clamp it. So you see the next move, it would be a soft clamp in two directions. I'm going to show you that move, but first I'm going to execute it. Once I execute it, it brings it back to its place. So showing you the soft clamp in two directions, I don't think I talked about this last time. You can apply a soft clamp in two directions, basically in the plane of the hole. It will constrain in that direction and in that direction at the same time. That's what made our point come back to its location, but the point it's already having the torque on it, so there's tension in it. The soft clamp in two direction is very simply to add. It's just the same point, add it twice, and you set up the directions in which you want to constrain it. I go to summary, you see the two directions. One is pure Y and one is pretty much in X. And you set up these directions. So once I brought that point back to its location, the next move would be I'm torquing this bolt now. Same idea as the first torque. And then I am going to soft clamp it, but in only one direction. So I'm not going to force this point in this direction. I'm just going to force it back to overlap with the hole in just Y direction. Okay? And then the next move would be to make sure that these 2 points are overlapping in one direction. So at this moment, these points are constrained in Z and in Y. It's free to move in X. Same this point. And once this scenario is concluded, I'm going to secure the bolts here at the front bracket. There's one bolt and there's the other. Now there's a difference between these two moves. I'm trying to keep everything with a soft clamp so I don't introduce extra tension. I let the fender slide wherever it needs to slide based on the constraints. The last of the moves, I am doing it as a hard clamp. There's a reason for that. Most of the time, if you have only soft clamps on your model, in nominal build, it can be fully constrained. But once you start adding variation, you add tolerances, the parts deform, they flex because of the tolerances and the moves, you can end up in a situation where your parts are not completely constrained. We do issue a message for that, so we tell you that your parts are not constrained. What does it mean? It means that your parts may not stay where you want them to stay, and you will end up with probably more variation than it actually happens in real life. So to avoid that situation, the last clamp, I made it a hard clamp. That will not influence anything that happened before in my fender, but it assures me that I have the fender staying in one place. And then I am going to unclamp the original hard clamp. Let it go. Let the fender spring back wherever it needs to spring back. I do have a contact move. Not sure if I talked about it last time. Contact move basically eliminates interference. I'm not sure it's an interference here or not at this moment, but I did add it as an example. It's very easy to use. You add the features, the object, and the target paired, and it will check the interference between object and target along the target vector direction. Again, we use the target vector. If there's an interference, then it will shift the object. If there's no interference, then it just doesn't do anything. And that would be the first scenario. Any questions? Are there any questions about this? If not, I'm going to move on to the second scenario, which is very similar to it. The one difference is instead of torquing this bolt, the front bolt first, I am torquing the rear bolt first.
All right, Maria.
So that's, yes.
Yeah, do you mind if I have a question or two real quick?
No, of course.
So question came in, what is plotted in the contour plot? The average variations considering the Monte Carlo runs?
Yeah, let me build it. Because now it's 0 because I don't have any variation. So there we have variation.
Is that?
Contour plot. Yeah, you can see that better, right?
Yes.
So the largest number is 162. The lowest is 0. 0 means no variation. 162 means the largest variation, where you can see here at the darkest area. So basically that this is the Six Sigma. Let me make sure of it. So these are the icons that we use for it. And it's the percentage out of spec. If I say, for example, estimated range, that should update shortly. Maybe separate the nominal build. I thought it, did I change it? Yeah. Okay. So the numbers here, they show you where and how much the largest deviation is. For example, if I'm going to turn on the second option, second set of moves, and turn off the first one, and I'm going to nominal build it now, the things should change slightly. Sorry about that. So with the first option, you can see the largest deviation is 0.89. Before it was 162. The largest deviation before was in this area. So this is what twisted more. Now it's somewhere here and here, which I suppose it's better. Maybe not better for this particular area which is going to meet the headlamp, but this area is also important because you attach the headlamp to it. So with both scenarios, we affect the attachment to the headlamp, either the attachment points or the gap to it. But in the second scenario, the variation is 0.89 instead of 162. So this still looks better for this area, for this particular area. Now, excuse me. In this area where we measured, it's a totally different thing because we measured this gap. We didn't look at what happens with the bracket here. So for these measurements, the first scenario is better. But for this area, if we go back to the model, the second scenario is, yes, the second scenario is better. So you'll have to pick and choose when you build a model and add all the measurements that are important to you. For example, like I said, I had only the back measurements. But if this flange is important, then you want to measure that flange and then weigh your options, so to speak. Which of the two versions will actually give you best results overall? That make sense?
All right, thank you, Maria. I appreciate it. I think that's pretty good. Just to summarize real quick on some of our compliant modeler, to give Maria a chance to get a drink of water.
Sorry.
No, you're fine. You're fine. You've been talking nonstop for a while, so just take a quick breather. So our compliant moves change your nominal position of your parts, so that you can
definitely, yes.
Yeah, Monte Carlo analysis is then run using the new nominal position, and that compounds your part and manufacturing tolerances with your compliant moves. So
yes, everything comes in play. I mean, your rigid moves will put the parts in their nominal. The compliant moves depends on what they do, but yes, they will change the nominal of your features, certain areas, yeah, because they twist the parts.
Perfect. Okay, well, we only have a couple, we're running a little short on time, so let's move on to your next scenario and finish this particular model, and then we can answer some of these other questions after that.
Yeah, I believe I did cover both, but yes, the idea, coming back to the beginning, the idea was front bolt versus rear bolt. Which one should be twisted first? And going back to the charts, very, very crude charts, it tells you that during the front bolt, our gaps are better. It shows a lot of red here, which from our model, we understand that if we use the second scenario, that whole variation goes away. This turned green, which means it went from, what was it? It was 162. It went to like 0.5, right? This area. That's what the green tells you. So building a model like this and using the color contour, it can give you a really good picture of where your variation is showing, and then you can concentrate onto that area. Okay? I think that should cover it.
Thank you, Maria. I appreciate it. So, so just to summarize again real quick, you did the 2 bolts after you attached the part, and you were checking the order on which bolt was best to do first. And which one did you find was better to start with?
For the gaps at the back, the bolt at the front.
Okay, so it's better to
and that was the objective of this model. Now, I'm going to go back to this color contour. See, with the same scenario of clamps and everything else, if we switch between the order of the bolts, and I'm turning on the second bolt, I'm building it. I mean, the first, I'm sorry. That's the first set of bolts active. The color in this area changed. Most of the fender is blue, which means there's almost no deformation when I'm driving this bolt first. The most variation is pushed here. At the same time, if I go to the Excel sheet, for the same second scenario, which is the green line, I get more variation. So the model tells me that my second scenario, which was before, was better here, and my first scenario, it's better here. So if you drive this bolt first, you get better, less variation at the back. If you drive this bolt first, you get more variation at the front, basically. Okay?
That's great. Thank you, Maria. I appreciate it. So we're at noon now, so I just want to make a couple of quick comments. One, I want to remind everyone that I will be sending the recording out tomorrow with some support material. You can get that material in the handout section right now in your interface. That includes some of the what's new for version 7.4, as well as a copy of the presentation and some of the results we have and some easy-to-read management reports. I do want to bring up a couple of questions, but since we're at the top of the hour, I want to first thank everybody for coming today. I appreciate it very much. Please take a moment to fill out the survey when you exit the webinar. It would be very helpful to us, and it's only about 4 or 5 quick questions. We just want some of your input to make sure that when we're making these webinars, we're including the information that you find helpful and topics that are most useful to you, rather than going off of what we feel is best for our customers. So please give us some feedback. Let us know what you want to see, and we'll make sure to make webinars based on those topics. Once again, I want to thank everybody for coming today. Appreciate it very much, and thank you, Maria, for giving us a wonderful webinar today. I'm going to spend a few minutes now just answering a couple of questions we had that came in, and then we'll close the webinar out for everybody. So some of these questions we've answered kind of on the side here. I've got Sarv helping me out because they're pretty generic or specific to the moves that you're using, but they're very good questions. So I want to make sure that everybody is able to get the answers to these. And some, well, let's just start at the top. So one of the things that one of our guests noticed was that there are points which are not used on the surface of the parts, but are still used for clamping and torque. And that's correct. So not all points have to be on the surface of the parts to be used. I believe in FEA there's a requirement for that, and we do not have that same requirement. Another question that came up is, can the DOE, the design of experiments, which allows you to run multiple scenarios in a simulation, can that account for clamp position variation together with weld or join order? And the answer to that is yes. So you can use some of these other DOE and in batch in order to run a number of different scenarios. Does the contact move consider several contacts simultaneously? So this was something that we didn't have before. One of the scenarios that you showed, Maria, was doing 5 joins at the same time, 5 welds simultaneously, and that was on the aircraft skin model. And we can account for all of those moves at the same time. So you can have multiple contact or join moves simultaneously.
Yes. Yes, of course. There's 2 points in here, for example, in the same contact move, and it looks at both of them.
Right. Because
if you have 100 pairs, it looks at 100 pairs.
Oh, wow. Okay. Because if you're doing them in order, it's going to push the variation across the part. If you do them all simultaneously, it's going to spread that out across the whole part.
Yes, and the contact move is not a permanent move. So let's say you put a contact move and you put another pair in a different contact move. It may cancel the first one. The contact move is not a permanent operation. It pulls the parts away from each other, but if you put something in other move after it, you can cancel it.
Oh. Huh.
Okay.
Since the
You can use a position afterwards if you want to hold the points in place where the contact move put them. You can do that.
Thank you, Maria. I'm sorry, we have a lot of these, so I'm going to be moving a little bit of haste. This is really important, actually, that I should have mentioned earlier. Since the compliant modeler takes more time to calculate, are there any plans to make it utilize multi-core processors? And the answer is yes.
Yeah.
In fact, that's in development right this moment, and we're hoping to roll it out soon. We're also talking about parallel processing, allowing you to set up a bank of machines, computers that you can use to just to run your simulations, and the option of a service which we would allow you to use to take advantage of a bank of computers for parallel processing in case you don't have any on site. So you could set up your model, and then you could set up your analysis, and then send the analysis out to this bank of computers in the cloud that would be using, of course, a secure facility, and it would turn out your results in a much faster period of time than running it on a single machine. So that's all in process right now. I'm hoping to have some announcements about that soon. Please just keep an eye on the newsletter, and you'll be able to see. I'll do a blog post as soon as I have more information about that to keep you informed. All right, so I've got a couple more questions. One is just a yes, no. Is elasticity considered in the simulation? And the answer to that is yes. And then how is torque different than a hard clamp, especially if using a soft clamp after torque? And that has more to do with the direction of the force. So a torque move, so you saw there's a choice between force and torque, because force is a single directional force effect, while torque is a rotational force. So on this particular part, when you're using torque, it's going to twist the part as you're screwing in that bolt. Is that correct, Maria?
Yes, yes. The torque just rotates the part, rotates the point around its axis along that vector by the number that you put in there, by the value of the torque. Now, soft clamp is just the translation. It just pulls the part. Yeah, that's the value of the torque. And they can work together.
All right,
that's why I put them that way.
Let's do 2 more questions, and then I'm going to take the remainder offline, as I don't want to keep everybody too long here. So some joints can have an inner variability, such as pin in an oversized hole. What happens in this case? How do you account for it? So this is like, I think, a pin float, or a whole pin float. So they're asking if I want to do torque and combined with whole pin float, how would I consider that? Do you
Well, we do not account for float inside any of the compliant moves. We do float the part. If you want to do that, you can float the part with a rigid move.
Right.
And then once it's established in its position, then you can apply the torque and, the compliant moves. But yes, the float is applied with rigid moves so far.
So we talked about this in our last webinar. I believe that the best way, the best practice would be to do your whole pin float rigid body move, and then apply your torque compliant move in conjunction with it. And that would give you a whole pin float in conjunction with torque.
Yes, that's correct.
Okay. Okay. I'm sorry, what was that? Yeah, we're not going to, all right, I'm going to take this last question, this next question offline, I think. Let's see here. All right, I think we're a couple minutes past it. Yeah, we're almost 10 minutes past the hour. So I'm going to close down the webinar at this time. When you receive that follow-up email, if you have additional questions, feel free to reply to it. If you had a question that wasn't answered today, I'm going to be following up with you right after this event and see if we can't help you out. As always, keep an eye on our newsletter for upcoming webinars. Like I said, we have our next one at the end of April. And thank you again for joining us today. I appreciate it. Maria, thank you so much for your time. Thank you for your presentation.
My pleasure.
All right, I'll be closing the webinar out now.